Good afternoon, everybody. Welcome to this webinar entitled Beam Shaping in Lasers for Material Processing. This webinar is organized by the Israeli Forum of Laser Material Processing that operates at the Association of Engineers and Architects in Israel, AEAI. This forum is one among many other professional forums acting at AEAI on the purpose of being professional network for engineers and scientists from different disciplines. The AEAI organizes seminars, symposia, and courses that gather together thousands of engineers from the industry, academy, and research institutes to exchange basic and scientific knowledge and know-how. My name is Shosh Tamir, and I am the head of the Israeli Forum of Laser Processing, or Laser Material Processing. The Israeli Forum is endorsed by the European Material Research Society, where you can find announcement of this webinar and other activities. We are very pleased to meet you today and to hear three speakers that have many years of experience in the development of lasers and laser application for material processing. As mentioned above, our topic for today is beam shaping in lasers for material processing. This is an exciting field that opens new possibilities in welding, cutting, and metal additive manufacturing. In the following talks, we will hear about the potential of this technology and existing solutions in the market. The webinar consists of three presentations, 20 minutes each. At the end, we will have 30 minutes for the speaker to answer your questions. The participants are invited to submit questions either in the Q&A key or by the chat. We encourage you to write your question during the talks. The first speaker is PD Dr. Rudolf Weber, Rudi, who is the head of process development IFSW, University of Stuttgart. His talk topic is the influence of static and dynamic beam shaping on the laser welding process. Dr. Weber received his PhD in 1988 at the Institute of Applied Physics, IAP, of the University of Bern on the subject of X-ray emission from laser-generated plasma. In the following years, he headed the research group Diode-Pumped Solid-State Laser and Laser Material Processing at the IAP. Since 2008, he is a lecturer at the University of Stuttgart and head of the Process Development Group at the IFSW, Institute for Laser Tools. Rudi, please.
Okay. Thank you very much for the introduction, and thank you very much for the invitation to give a talk and an overview here over our work we are doing at the IFSW on beam shaping. And in this case, on laser processing, you introduced myself, but basically all the work I'm going to present was done by these people here. So I'm just the one who shows what's going on and not the one who does the work. You see there is a lot of people involved. You are doing a lot of time already, or working a lot of time already on this topic. The Institute itself at the University of Stuttgart was founded more than 30 years ago, 1986. And from the beginning on, it was a kind of holistic approach where lasers and laser development was addressed, as well as the applications. And meanwhile, we also have a small systems group which tries to fill the gap in between these two fields here. Actually, we have 48 employees in the Institute, and 34 of them are the academic staff really doing the academic work. What is important to know is that we have about 80% of third-party funding, so we do not just rely on government money. We really, a lot of time, work like a small company. Actually, we do about 50 student theses, and this is the new currency for institutes, citations per year, where you can get money if you have a lot of. Actually, we have about we have more than about 500 citations. So this was only the short introduction to the Institute. I learned that a lot of you are not really familiar with laser and laser welding, that you have a huge knowledge, but not on this specific topic. So I'm also going to give a short introduction about what we are going to talk today. Today it's mainly welding, laser welding. This is a typical arrangement, a film which was made by Trump a few years ago. We have the laser standing somewhere. We have this light cable where the light is going into the processing optics. We have some protective gas here. And then in quite a big distance, up to a meter maybe, we have the sample. In this video. It's a car door, which is welded. And that's how it looks. If you look at the process, the whole system moves around, and then you can see that wherever it's getting bright, you see that there is some welding done. And of course, today it's interesting to have a closer look on what is going on here. And as you might not be that familiar with this process, this could be the car door. This is the surface. We have the laser coming from top and moving slightly to the right. And let's go back again, because it looks nice. Then you can see that we create some metal vapor. The laser heats the system up to boiling temperature. We create vapor, and the vapor pressure presses the melt away, creating a kind of capillary, as it's called. And what is important with this capillaries, it's quite deep, and the laser, if you look at it as rays, you can see that there are multiple reflections inside this capillary, which makes that almost all the energy which is in the laser beam is coupled into the process, which makes the process very efficient and very useful for deep welds. We have some melt pool where the material is molten, and then after a certain time or certain space during the movement here, it resolidifies, and what we get is some weld seam, of course, which might look like this. This is a typical cross section of a nice weld. This is the surface. That's where the material was molten. And what you can easily do with laser is that it's much deeper than wide. And this can be done very fast. And of course, this introduction says laser welding is very nice. It's a very useful process. It's also very often used in industries already, as you might have seen with the car door, but it's also very challenging. If you look a little bit closer, you see there is a lot of fluctuations, which might yield to long welding depths or long cross sections of the joint. This is one of the issues. The other thing, if you look a little bit closer, you can see that there is a very nice crack building up at the end of the weld. Of course, usually you don't want to have such a crack. And also you can see there is big and small spatters emerging from this bubbling liquid here, which is the metal surface. And in my talk, this is more or less the contents of my talk. I want to say a few words about these three topics, and of course, what's going on with the laser beam. And if you have a closer look again, then today a typical standard, of course, it's not really standard, but the typical standard parameter set is we have here in the focus where the laser is focused onto, we have some top hat or sometimes some Gaussian intensity distribution. This is really common. That's usually done. And on the other hand, as you might see from this film already, the laser beam just moves linearly over the surface and doesn't make any additional movements or any additional power or intensity distribution changes during the weld. And of course, what is interesting today is, does it help if you start now moving such things like the beam, or if you start creating fancy intensity distributions to influence your process? And of course, one of the questions is how can you prove that it helps? And for this, we are in the happy situation at the IFSW that we have this, as we call the IFSW X-ray facility, which provides some insight into the process. This is a LED housing, quite big, with the commando, the operator's stage here. It's made of lead. Inside we have full process capabilities, including laser. Here the yellow thing is the light cable. Here the process head would be, and a lot of axes to move everything around. We have gas supplement to also work with process gases. And what is really the nice thing about this is we have an X-ray tube, a point source X-ray tube, and a scintillator with a high-speed camera where we can X-ray the whole process during the process. And of course, we have other things like high-speed cameras. And finally, we do image processing to understand what is going on. And that's how it looks like. Let's go back one picture again, sorry. Here you can see this is a typical sample. This is the surface. The laser comes from the top. The X-ray comes from the side. And the high-speed camera looks from the top. So what you can see here is, this is the surface of the sample. In this case, it was aluminum. Here we have a high-speed video with 1000 frames. And the lower part is, again, the aluminum part. Here is the upper surface. Here is a stop to prevent overexposure. And here is the bulk material. And what we see here is the X-ray video, now also with 1000 Hertz. And that's how it looks like. This is the laser beam coming. You see that on the top, you get an explosion. The process starts. We get a nice capillary. So whatever is brighter, material is missing. And what you can see is the capillary I've explained just before. And here the laser beam is coupled into the capillary and the system is heating up. And that's what you can see now, that it's very fluctuating. We can see that whenever it's bright here, it's a kind of bubble or a kind of pore finally. And you might also see that the contrast is not very good. That has something to do with the complete X-ray system. Therefore, we have here a drilling. This is a mechanical drilling, which is filled with tungsten powder, which does not melt. And what you can visualize now is what's going on inside the melt. So you see, whenever we go with the beam through this tungsten powder, you can really nicely see how chaotic, let's say, the whole fluid flow in this hot molten aluminum is, how you create eddies, and also how you create a lot much of pores. So this is an idea. You will see today a lot of such images and pictures that you get an understanding where we come from. So come to now to what is the benefit of beam shaping. And the first very, very simple example is shown here. This is one of the typical automotive applications of today. You have some aluminum sheet which should be welded to a copper substrate. And of course, the cross section here at the interface between the two metals is essential for the mechanical and the electrical properties of the whole system. And if we have now this straight moving beam shown here as a sketch, this is what we end up with such a weld. So this is a cross section, the same as here, this grinded, that you can see what is going on. On the darker material here is the aluminum, on the bottom the brighter is copper. And this, what you can see here, is the laser weld which was done. This was already a very nice and very good weld. You can see that only a few copper is molten, which is important to have a good conductivity. But what you also can see is that the cross section is quite small, and also that the copper is distributed all over the weld. And now what you can do is the most simple beam shaping, or one of the most simple beam shaping things is you do wobbling, which means that during the moving of the beam, you have an additional movement of the beam perpendicular to the movement of the direction. So this then ends up with a quite wider weld seam. Here are the parameters for those who are interested. And you can see that the beam is moving here from left to the right, while the whole beam then is moving to the bottom to top, while the whole thing is moving to the right. And this is how then the weld looks like. If everything is adjusted well, you can see that the seam now is much wider, that we have a very nice, at most of the parts, you have a very nice cross section here where the current can flow through. And you can also see that the mixture of the material up here in the remainder or in the rest of the weld seam is very low. So this is a very nice weld, which you can achieve by simply moving the beam over a surface, by having also, of course, the right power, the right frequency, and everything must be adjusted. If we just wobble, nothing happens. So it's really important to have the correct parameters. So we have a defined penetration depth, much more defined than here, and we have quite homogeneous mixing, so which means we can really improve the mechanical and the electrical properties of such joints. The second thing I would like to show you is the formation of hot cracks, which is also a quite important issue that mainly happens if you do close edge welding of aluminum alloys, which is mainly in car doors. Modern car doors are made of aluminum. If you are close to the edge in a few millimeters distance, that's what happens if you do just a straightforward weld. You can see that really very short after the solidification here, a very nice, very big crack opens. You can make this cross section with Parker etching. Then you can see the material structure which comes up. We have a narrow band with equiax dendrites, so-called, so kind of balls, and we have a kind of fingers here pointing to the center, which are called oriented dendrites. And the problem is, if this zone is very small or even does not exist, then we have these two fingers being very close to each other, which then very much favors the arising of such hot cracks because the mechanical strength is quite low. To understand how to solve the problem, you must do some material science, very simple, just a short look at the solidification map. Here is the solidification rate, R in millimeters per second. Here is the local temperature gradient, G in Kelvin per millimeters. And then you can create such a map where you see that here in this part, we get this equiax dendrites. And here in the lower part, we get this oriented dendrite. So if you want to have strong, stable welds, we must come in this range here. And the question is now how to get there. And to understand what is going on, that's, let's say, not so simple. So it's a big effort to find it out. Again, we use our diagnostics. We have a look from the top at the weld. We have a look from the side at the weld. And then with correct image processing, we can define where we have the solidus line here from the top and here from the bottom. That means where everything is liquid. We have the liquidus line, sorry, here we have the solidus line, where everything is solid again. And now this I want to show, we do some modeling, now numerical modeling, which we calibrate with these films. And then we can determine the local R and local G. And you can easily understand that here in the side, we have a low R, which means we have a low solidification rate, but a very high temperature gradient on this side. So we would end up in this region with the dendrites, with the oriented, and at the back of the weld, we would be in where we have a high R, so a high rate and a low temperature gradient, we would end up here. And the trick is now to adjust everything and to understand the process parameters to really get here and get here. And this can be done. This is again the linear weld I have shown already, small equiax region and a large oriented region. Again, wobbling is one of the first means that you can apply. And what you see here is that the oriented part is almost constant. It does not grow or diminish, but what you can easily do by doing the right wobbling, right power, right feed, and so on, you can achieve that you get a much larger area of equiaxed grains, which means this weld is much stronger than this weld. And of course, one can go further. The next is, in addition to just wobbling, you can also make power and feed modification, which means when you get slower, you decrease the power. When you get faster, you increase the power, which also then changes the solidification conditions here drastically. And you can see that we could even achieve that we have in the middle, we have no equiax grains, then we have a wide area of equiax grains, and again back, even no equiax grains. So this is at the close-up. So by doing this, you can even change the material properties doing welding. And if some crack might occur here, we might stop it by changing the material. This was already shown. And of course, you are not completely happy with our weld. We are also not completely happy with our weld. Now, the next thing to address is transversal cracks, which is still not solved. So this is one of the open problems that has to be solved, that we now, as we can avoid the longitudinal cracks, we still have the transversal ones. There must be open questions, otherwise we wouldn't have anything to do. And the third thing I wanted to show is what happens with spattering. I showed you that this is a very fluctuating process. And typically we have two regimes where spattering occurs. We have here in this part, we have small fast spatters. You see that they're emerging here from the melt pool very fast. And here we have a lot of big drops. Sometimes this is bad, sometimes this is bad. However, usually people do not want to have spatters. So what happens? If you look at the X-ray again, now in false color, you see that we have, in this case, we have a very deep and very narrow keyhole. If the keyhole is so narrow, this means that the vapor which is created down here with the laser has to emerge very fast. You all know Bernoulli's law, of course. If the cross-section is small, the vapor has to emerge very fast. This fast vapor makes friction here on the surface and tears away very small droplets which originate here from the surface inside the capillary. So in this case, we have a lot of small and fast spatters. This is completely different. Now the capillary is wide and inclined a little bit to the back. And what I cannot show, but you have to believe me, there is a strong eddy behind the capillary, which is not the case here. A very strong eddy which moves the whole liquid up, and if the surface tension is not enough to hold back the liquid, you see that we have really large droplets which just blow out here of the complete system. So with the large and inclined capillary at higher speeds, you have to compare the welding speeds also, we can create these large bubbles. And now to another system of beam shaping. This was originally presented by Trumpf, called bright line weld. This is a two-core fiber. We have an inner core and an outer core, and the power can be distributed between the two cores, which is schematically shown here. For example, you can make that everything is here in the inner core. You have something which is a little bit around, or you have most of the thing in the outer core. Even larger doesn't make sense. And if you now look at the number of spatters for these three intensity distributions, you see that here we have very much spatters where 100% is in the inner part. Here at 70, when you have a little bit around of the hot spot here, a little bit around, then it dramatically drops, and then it comes up again if you have the large spot. And it's not very surprising that I was showing these images before. So this is the capillary which was created when everything is in the inner core. This was the capillary which was created at the higher speed when everything was in the outer core. And in between, and you remember here we had fast and small spatters, here we had large and big spatters. So there is of course a stage in between where we, with this small ring, we slightly open the capillary, which means the flow velocity dramatically drops, and the number of large spatters is decreased, of small fast, and the large did not come yet because the capillary is still narrow and deep. Very simple, very effective means to reduce spattering. And the last thing is only because it's nice. I would like to show you. We also had a lot of pores, and Eric Punzel will then explain everything about pores in his talk after myself. But I have a film which he does not have. That's how it looks inside such a weld, by the way. You create a lot of pores. This is typical automotive weld parameters, 3.4 kilowatt, 4 meters per minute. So that's how it looks. You also see that it's not very constant. However, the nice thing is, another possibility is some circular wobbling. You just move the beam around. That's how it looks like. This is the parameters again. 200 Hertz was nice. And that's how it looks inside the weld then. And what you can see is that the capillary is here moving around. This is the capillary here. And at a certain point, a pore is created. And after the next round, you see that the capillary is coming back and eats up the pore again. So you can create the Pac-Man, or there might be some older people among you who still know Pac-Man. It really looks like this. The serious message for this film is, even when you create pores with the appropriate means, you can go back and outgas. Pores only exist if you have gas in, you can outgas the pores. So, does beam shaping help? Was the question in the beginning. I think yes, it helps really a lot. For example, very simple, you can have better functionality. You can influence how you solidify the grain structure that you create, and you can also very strongly reduce spattering, and pores will be shown then later on. So I think this is my opinion for today, that the beam shaping is really the means which is absolutely necessary. I mean, it's not only my opinion, is necessary to get really perfect welds in future. So this was my message for today. Thanks for the attention. Thank
you very much, Rudy, for a very nice presentation and very interesting. We are now moving, the question will be at the end of the 3 presentations. So now the next speaker is Mr. Eric Punzel from the R&D team of BBW Lasertechnik company. His talk topic is the influence of power distribution on weld quality and geometry in the laser beam welding of aluminum alloys. Mr. Eric Punzel, MSc, studies physical engineering, laser technology in Mitwidia, Germany. Currently, he is working as a process development engineer at the BBW Lasertechnik for several years and responsible for feasibility studies in laser welding, cutting, and ultra short pulse machining, as well as the project management for national and international R&D projects. Please, Eric.
Thank you very much for the introduction. I hope you can hear me all and you can already see the presentation.
You are well heard and we can see
Perfect. It. All right. Yeah. Thank you very much for the presentation. I want to continue with the question where Professor Rudolf Weber has stopped, and I want to continue and try to give the answer. Yes, it will. Beam shaping will improve, will help us. So today's topic is, for me, what I want to show you, influence of power distribution on weld seam quality and geometry in laser beam welding of aluminum alloys. Especially, we want to take a look into the pore generation and how it is possible to avoid them in the best case. So, one moment. Okay. So, at the beginning, I would like to introduce my company, BBW. After that, we will have some talk about the already mentioned topic, the generation of process pores during laser deep welding. Shortly, we will talk about known strategies for a decrease of pore generation. And after that, I would like to present some experimental in-house results for laser welding with the variable power distribution using a 2-in-1 fiber. This is the Brightline technology we already have seen in the presentation before. Something about BBW Lasertechnik. We are a company in Germany, in the southern part of Germany, in Bavaria. It's near the mountains, the Alps. The company was founded 23 years ago and assigns then a pore job shopper of laser material processing. And our main topics here are laser welding, cutting, drilling, marking, and USP processing. BBW has started in a room with just 40 square meters, several moves and extensions has made. Okay, it has moved without I did something. Yeah, with the finished building of the fourth production hall last year, BBW has now more than 8,500 square meters of production and office area. We have currently 150 staff members and around 43 laser systems. And 2/3 of these laser systems are used for laser welding. A significant part of these laser systems are also not purchased complete solutions, like for example from Trumpf, but they have been built internally. So for ensuring the part reproducibility in a series, we have also an internal construction department for fixtures and a quality assurance department, including a metallographic laboratory as well. And most of the results you see today also come from in-house production and from our metallographic laboratory. Last but not least, of course, the process development team is mentioned, where I'm part of it since 3 years. We accompany the feasibility studies and process development for new prototype components. So compared to a university or an institute, our work may mainly focus on production improvement, but we take also part in R&D projects together with these partners in national and international bases. So far, this was something about the company. Now let's go into the main topic. We have seen already very nice theoretical and practically views into the laser deep welding. So I can skip some things. So with the laser deep welding, a zone of vaporized material, the so-called vapor capillary or keyhole, is created in the laser matter interaction area due to the higher intensity of the radiation. And the stability of the keyhole is maintained by a pressure balance of various acting forces in the material and the defined processing speed. The liquid melt flows around the open keyhole and finally solidifies as a joining weld metal behind the moving laser beam when cooling down. It is assumed that the keyhole dynamic behavior, like absorption fluctuations or local soiling, is the origin of defects like pore generation. When the vapor capillary becomes unstable during laser welding, a gas bubble can be formed and trapped inside of the solidified material. And this is very nice visible here in these pictures. I must tell I have stolen these images from Professor Weber because there are only 3 spots in the world known where you can watch laser processes with an X-ray image, and one spot is the IFSW Stuttgart. So you can see here in these images that a bubble is formed because the vapor capillary collapses on the lower part, and this bubble is not able to go up on the surface fast enough, so the material solidifies and the bubble is trapped as a pore. And pore inclusion is one of the critical welding defects and will affect the strengthening of a part. So the mission is clear. We need to avoid pore inclusion completely, or when it's not possible, decrease the porosity in a welding zone, a fusion zone. So there are different strategies against pore formation, and I want to show you some of them. Some are already well investigated. One of them is wobble welding. We have also already seen how wobble welding works. So I just show you what happens when we use wobble welding for the decrease of porosity. As you can see in this image, there is still the pore formation during wobble welding. But by using a circular oscillation geometry here, the beam passes over the same position several times and interacts with possible bubbles multiple times. And this leads to the disappear by degassing back into the capillary and is the reason for significant pore reduction. And on the right side, you can now see some cross sections we have made. On the top, we have a cross section for a weld seam without the wobbling technology. We have here relative porosity of around 2.5%. On the bottom, you see another cross section for a weld seam with exactly the same parameters, but with additional wobble technology. So here you can see the welding depth is a little bit lower, but also the porosity is significantly decreased from 2.5% down to 0.6%. Another possibility is high-speed welding. This also reduces several weld irregularities. And again, some X-ray analysis from the IFSW Stuttgart. We see here a widening of the vapor capillary, which leads to a more stabilized capillary itself. And fluctuations of the capillary decreases with increasing feed rate, and the capillary opens more. And at 50 meters per minute, there is a completely different geometry. This could be a huge presentation itself about this topic. So what was here achieved is nearly no pore generation, but there are other disadvantages at this speed. We go into a regime where humping effects occurs. And there's also another disadvantage when we weld a material with a hot cracking tendency. We have the problem that the hot crack tendency increases mostly with higher welding speed. Here we see another possible strategy, the usage of a superimposed intensity distribution by different laser spots. The idea of the so-called double focus technology is the widening of the vapor capillary for a better keyhole stability and requires either the splitting of a laser beam or using two different laser beams. Or you just have a laser source which is able to create multiple spots in a very fast time. We would like to add here our own investigations with the 2-in-1 fiber, so the bright line technology, which also superimposes two beams, but in a concentrical way. And we have already talked about this. The approach here is, so bright line is just one technology from Trumpf. There are also other technologies which do mostly the same, like AMB from the company IPG, IRM from Coherent, or Corona from Enlight. It's really called Corona. The idea here is we have a variable power distribution between a core and a ring fiber using the 2-in-1 fiber. So we promises here improved seam quality, reduced spatter formation. We have seen already that it, of course, reduces the spatter formation and increased welding depth. During laser deep welding, a widening and stabilization of the vapor keyhole is realized due to the power distribution of the ring fiber. So the molten material around the keyhole is influenced from the ring beam power with a contrary impulse and deflected to the backside of the keyhole. So for our experimental investigations, a Trumpf true disc laser with 4 kilowatt and a bright line weld module was used. The laser beam was focused to a spot diameter of 200 micrometer of the inner core and 800 micrometer of the outer ring fiber. The pore the power distribution inner core to outer ring can be varied between 100 to 0 to the opposite 0 to 100. For our investigations, we have used a very low welding speed of 2 meters per minute. At this speed, you get images like this. Of course, this is not optimal for a low porosity, but we can see here very well an improvement when we change other parameters. The upper left figure gives an example of different power distributions that can be generated with a dual core fiber. Since the diameter of the inner core is much smaller than the outer ring, the intensity in the inner ring is usually much larger than in the outer core. For example, a power distribution of inner core to outer ring of 75 to 25% with the configuration shown in this table here, 900 watt to 300 watt, leads to an intensity distribution of 29 to 1. In order to determine the influence of power distribution of inner core and outer ring on penetration depth and weld seam width, the power distribution is varied while the total laser power is kept constant at 900 watt. The results for penetration depth are displayed in the left figure. We have investigated different aluminum alloys here, and for the alloy AW1050, this is pore aluminum. The process is in the welding regime of conduction mode welding for a laser power of lower than 500 watt, and for alloys AW6082 and 5083, deep welding begins at a laser power of around 400 watt with a deeper penetration for AW5083. The reason for this behavior is the lower evaporation temperature and thermal conductivity for aluminum alloys with a higher content of other elements. The penetration depth increases linearly with laser power of the inner core. And in contrast to the penetration depth, the weld seam width is not increasing linearly, what you can see here on the right side. The graph flattens at a higher laser power, indicating that for higher laser power of the inner core, only penetration depth increases, but weld seam width reaches a saturation. So the porosity is at 12% for the power distribution of 100% into the core fiber. And it decreases for power distributions 90 to 10 and 75 to 25% to a porosity of around 8%. So with increasing power feeding into the outer ring, the porosity increases again. And the highest porosity is measured with a power distribution of 25 to 75. So it is very possible that a minimum optimal parameter set exists between 90 to 10 and 75 to 25%. The maximum pore size is displayed in the middle figure for different power distributions. Maximum pore size is very similar for power distributions 100 to 0 to 75 to 25%. It increases with further power fraction into the outer ring. This is maybe because of the larger vapor capillary. Larger bulges exist at the bottom of the capillary, which could lead to larger pores. In the right figure, there is a comparison of two longitudinal sections with a power distribution of 100 to 0, so 100% of power in the core, and 75 to 25%. And you can see here very good what I already have told you, that the porosity is clearly decreasing. The porosity can be improved further, and we must do this also by combining with other strategies. For example, high-speed welding. And this is what we can check here. We went here into a very high-speed welding profile. We have used here a welding speed of 26 meters per minute and the power distribution of 75 to 25% with the 2-in-1 fiber. So we enable here almost no pore formation. We did different cross sections. Unfortunately, I have for this presentation no longitudinal cross sections. But as already mentioned in the beginning, we could come into another process window with a higher probability for hot cracks for some aluminum alloys, which is exactly the example in this case. So for an understanding, we have milled down the surface near the weld seam, and we can see here in the weld seam small micro cracks. Therefore, process development is very often a balancing act, finding the right process window. In the conclusion, in terms of welding quality regulated by welding standards like the ISO 13992, this is for aluminum, we separate here between different quality classes B, C, and D, which means a decreasing quality from B to D. We achieve just with the with different power distributions an improvement from 12% porosity to 8%. This would improve the quality from not acceptable to class D according to the ISO standard. Since pore formation predominantly occurs at the bottom of the keyhole, the application of flexible power distribution porosity can be reduced but cannot be avoided completely. Here we must combine this strategy with another strategy. The results shows that penetration depth is also primarily dependent of the laser power of the inner core due to a much higher intensity, and it is assumed that the reason for the reduced porosity is therefore a reduced vapor velocity due to an increased keyhole opening. So I hope I could give a little insight into pore generation and how it could be possible to decrease the porosity in a weld seam. I'm open for questions. I will read now the questions in the chat, and later we also have some time for talk, I guess. Thank you very much for listening.
Thank you very much, Eric, for a very good presentation, very interesting. And now we are moving to the third presentation. It will be given by Dr. Eyal Shekel from Civan. He is the CEO of Advanced Technology. His topic is dynamic beam shaping for laser welding. Dr. Shekel is the founder and CEO of Civan Advanced Technology, the first company to develop industrial lasers based on coherent beam combining. Prior to Civan, Dr. Shekel founded Cielo, a leading company in the manufacture of fiber optical gyros navigation system, and founder and general manager of Cairo Network, which developed the largest optical switch in the world. Dr. Shekel was also the co-founder and board member of NanoOr, which developed and manufactured 3D measurement system with nanometer resolution for the semiconductor industry. Dr. Shekel received his PhD in physics at New York University. Eyal, please.
Thank you. Thank you very much, Shosh, for the introduction. So I'm actually very fortunate to give my talk after these two very good talks by Professor Weber and by Eric, because I think everybody now is convinced that beam shaping is very important for material processing. And we would like now to introduce our laser with the dynamic beam shaping. We are the only company in the world who is offering such a proposition of dynamic beam shaping at very high powers. And I would like to explain what it is and how it contributes to material processing. So just before I do that, just one slide about Civan. So what we do is manufacture lasers based on coherent beam combining, like was mentioned. We started operation in 2008. We are 180 employees. We have our building in Jerusalem, 3,500 square meters with clean rooms, manufacturing facilities, integration facilities, and so on. We've been selling lasers for many years, so we have a good track record with many leading customers. We're what's called a vertically integrated company, meaning that all the core technologies are done in-house. We have many patents, and we do a lot of research collaboration. So I would like to talk about our OPA laser. OPA stands for optical phased array. This is a type of coherent beam combining. And what we provide is high power, single mode lasers with dynamic beam shaping. And when I say high power, I mean tens of kilowatts. Single mode, I will have 2 slides to explain what single mode is to people who don't know. And then I will elaborate on the dynamic beam shaping. I just want to use the opportunity of this slide just to make 2 points. One is, like was presented right now by the 2 speakers before me, that beam shaping helps the process, but I think it was also clear and mentioned several times during the talks that you have to adjust the parameters. It's not so simple just to take one beam shape and all of a sudden everything works. For every process, you have to adjust the right parameters for the process. And everything that you change, whether it's speed rate or thickness of the material or coating of material or consistency, everything needs adjustment. And we are the only company who actually allows to adjust these parameters very, very dynamically, as I will explain. Another thing is, I think, is also shown that when you increase the feed rate, it's much better for porosity, for example. You get better results when the feed rate is higher, but when the feed rate goes higher, you also need more power. So the ability to provide all this at very high power is also very important. And when I say very high power, we can provide many tens of kilowatts. So first of all, to explain what is single mode. So single mode is really a Gaussian beam. A Gaussian beam has the smallest possible divergence, as opposed to a multi-mode beam, which is really composed from many modes in some combination between them. And what it does is, first of all, it allows to make a very small spot with a very deep depth of focus. So the beam is focused to a small spot, not only in one point, but also plus minus a few millimeters, which helps a lot in the process. Another thing is, because of the low divergence, it allows to work from very far. This is a picture of our application lab, where you see the laser beam comes out from here and goes 3 meters until the workpiece. So this gives a lot of flexibility, the fact that you can work at large distances. So what is the dynamic beam? So the dynamic beam shaping is the ability to manipulate the beam shape. Now, what exists today in the market, as was mentioned, was the Corona or the AMB of the different companies, which really allows to do a combination of a small spot with some kind of a ring shape, and to change the ratio of the power between the spot and the ring. But this is the extent of the flexibility that is available. Another way to do beam shaping is with some fixed optics. So either it's a regular optics or a DOE, and you can really make different shapes. The problem is that once you design a shape, you design an optics, you get one shape, and there's no ability to change that shape. The third method is using mechanical scanners. I think some of the results that Professor Weber showed with wobbling is actually done with mechanical scanners, but they have the limitation of the speed, what they can do. They also have the limitation that basically the beam goes continuously from point to point. There's only a limit of what shapes you can do. And the higher the power, it's more difficult on the mirrors to handle very high power. What we do in Civan is the dynamic beam shaping using electro-optical effect, coherent beam combining. And really, you can design any beam shape that you want. Basically, it's like using the laser as a pencil and drawing whatever picture you want. As you can see that it doesn't have to be continuous line. Like, I mean, here it's continuous, but you can have different points separated from one another. It can be any arbitrary shape, and it can be moving at different frequencies. So for example, you can have here a circle or a spiral, and this circle and spiral can go very, very fast or slow, whatever rate of change you want. Also, there's ability to do a sequence of shapes, meaning you can take different shapes and do them one after the other with just microseconds from one another. So it's really like a whole sequence of shapes one after the other. And the last thing is the ability to change the focal point of the laser, again, in a real time at very fast speed as you do the process itself. So I will say a few words about each one of these four categories. First of all, about the beam shaping. So we see here 3 examples. It's all bead on plate of 3mm stainless steel, where the only difference between these cross sections is what beam shape we used. Okay, so it's clear to see that each beam shape has a different effect on the material, and it really depends what you try to achieve. So you have some people have different requirements for different processes, but it's very easy just to go from one beam shape to the other. Another example, again, this is from our application lab, what was shown a lot before. You see here a spatter coming out compared to a very clean spatterless weld over here. So to do the different beam shapes, we have a very, very simple software. Basically, you go with the mouse and you click in a few places, and automatically you see a simulation of what the beam shape is going to look like. You just save the file, upload it to the laser, and you have the beam shape in the laser. So it really takes minutes to design any beam shape. You get exactly the simulation of what it's going to look like. You save the file, you upload it to the laser, and you can use it then whenever you want. In terms of the shape frequency, so just to better explain again what we're talking about. So for example, if you want to make this ring, if you make the laser go very fast, let's say at a megahertz or 50 megahertz going around, it's really quasi-static because it goes so fast, let's say at 50 megahertz, that in reality, just like a static beam at some shape. But you can also make it go at kilohertz or hertz or as slow as you want, and really do beam steering and kind of steer the melt pool as you go. As again was shown, you can go back to places and take out pores that were captured there and so on. So this is example again from our application lab, where you see again stainless steel 1.5 millimeter welding, where we use this infinity shape. Okay, and the only difference between the different welds is the frequency by which the beam was moving around. And it's clear to see that every weld is different. And again, it depends on what we try to achieve. So the point is just that it's flexible. You can really do in a minute, change the parameters and get different frequencies and get different cross sections. This is another example of doing 3 different frequencies. So you see this is a circle at 1 kilohertz, 5 kilohertz, and 20 kilohertz. Every time it passes by, you saw another bead on plate happening, and of course you can see clearly that there's a different behavior of the weld. You see here the line was created. You go again, you get another one, and so on, and really just changing the beam shape between one test to the other is just a click of a button, or you can reprogram it in advance. Another example of this beam steering is similar to what Professor Weber showed about welding aluminum to copper. And we have a very nice weld here with very little intermetallic mixing, a nice wide weld with having this infinity shape. So it's similar to the wobble, to the mechanical wobble, but here we can do it at any parameters, any speed, any width, and so on, just by a click of a button. And going from one type of weld to a different type of weld is, again, just changing the cross-section. And here we have a very deep penetration weld. Now, I'll talk about the sequencing. And when we say sequence, the idea is that, let's say you make here a set of 6 different shapes. You make 2 lines that are far away, a little bit closer, and so on. You just make these drawings, you save the file, so you have this shape saved, this shape saved, this shape, and so on. And then you make them go one after the other at whatever frequency you want. So you can change them slowly from one another or fast from one another. And of course, everything we're showing here is just for the presentation. In reality, you're talking about kilohertz, tens of kilohertz, or megahertz. You can have a microsecond between each shape. So these changes in shapes are very fast and controllable. So where are examples that one might want to use it? So first of all, you can make very complex beam shapes, okay? And this thing can happen at, again, tens of kilohertz or megahertz, and control the melt pool in very sophisticated way. You don't just like wobble it around, but you can really stir the melt pool whatever way you want. And this is just an example, artistic example, so to speak, but any shape that you want to do. By the way, all these images are at 10 kilowatts. These are all captured from our laser at 10 kilowatts. Another very important use for the sequence is this, for example, in additive manufacturing or when you do a shape. So, for example, if you decide that a good beam shape is 2 points, but you go on a trajectory on a part, the orientation of these 2 points always has to be perpendicular to the propagation direction of the laser. So you need to be able to rotate the beam shape. So rotation of the beam shape is also can be pre-programmed and done automatically in real time by the laser. And the last example I'll show for the importance of the sequence is, for example, if you want to drill a layered material. So if you have some metal with some ceramic on it and some glue in between them, the beam shape and the beam properties going through the ceramic or going through the metal would be completely different. So if it takes just 200 milliseconds or 300 milliseconds to drill the whole thickness, while you're drilling, you can change from one beam shape to a second beam shape to a third beam shape during this drill. So every few milliseconds, you drill to a different shape. And this, again, is, I think, nobody can get even close to this ability of changing the beam shape in a few milliseconds during a drill. And the last category is the focus steering. So this ability to change the focal position, again, at megahertz. So we're showing here 2 examples of cutting cross-section. On the top, we show a constant focus. So basically, the focal spot was somewhere in the middle, where in the bottom, we show focal steering, okay? And clearly, you can see both the effect of different beam shapes, okay? So this is with a single point as opposed to a spiral. and the difference between beam shaping or not, I mean, focus steering and not focus steering. So again, we're not saying that one is better than the other, each one has a different parameters, but the point is that we can control these parameters and optimize for the optimal process required. So in summary, we showed you 4 categories of the dynamic beam shaping. First of all, the ability to do any beam shape that we want, change the frequency of these shapes, do a sequence of shapes, and do focus steering. And really, we believe that this dynamic beam shaping opens completely new opportunities that are not available today in material processing. And again, there's a lot of research and optimization required for every process to get the right beam shape that is required, but our laser can allow a very easy adjustment of the beam shape to whatever is required. So just my last slide, these are our product lines. So we have the OPA6, which is available now up to 28 kilowatt. We also have a green laser, which we didn't discuss now. We also are now delivering the largest 100 kilowatt single mode laser. This is the largest single mode laser in the world. And this is the OPA20, which is not available yet, but we hope it's going to be available in a year or two, something like that. So thank you very much.
Thank you very much, Eyal. It was very, very interesting 3 presentation, and I hope the audience enjoyed this presentation. And now we are going to the questions. There was the first question was to Eric, I think, but he has already answered it. Is how do you wobble the laser beam? So you can see the answer for that. The second one is to Rudy. Is there any chemical or optical coating to optimize the control and control the melt pool and the debris? You see the question?
I see the question, and I guess I give it in spoken instead of writing. I thought that was the idea behind. I think you have to distinguish between the process itself, where you have a lot of hydrodynamics and aerodynamics, and the solidification. During the hydrodynamics, there is only a few things which can really influence the melt dynamics. You might know that the surface tension is a function of the temperature, which is called Marangoni. Then you get a force which might influence the flow of the melt. And by applying some process gas, you can change the direction, for example, of the Marangoni flow, which then also have some influence on what's going on in the fluctuating part of the process. In the solidificating part, then you can really add adding materials in case of aluminum and silicon that you can avoid, for example, hot cracking, or that means at least reduce hot cracking. So chemical means and coatings to reduce the process itself, the let's say spatter or what you mean debris or whatever. I don't see any chance, because the possibility to influence is not that big. So it's much better to shape the beam to influence the process itself. To influence the solidification, it makes sense sometimes to add things.
Thank you. To all panelists, kindly comment on different type of lasers in use. Please also state the input power needed.
Well, just use Civan lasers, it's clear.
Yeah, but what is in the market now, maybe?
Yeah. So typically today, everybody is using lasers at 1 micrometer wavelengths, which are fiber guided. these yellow cables I have shown in my talk. There is some fiber inside with a certain diameter, usually ranging between a few 10 micrometers to a few 100 micrometers. And on the input side of the fiber, there might be a fiber laser, there might be a so-called disc laser. Sometimes if the beam is big, there is even a direct diode laser. This doesn't really matter. Right? The source itself is partly a philosophic question, partly it's a commercial question, and there is only a small physical aspect on the different type of sources. But what is used, all these fibers are, all these lasers are fiber guided, that you can go to the process. Usually, you must be close to the process, to the processing head. So the fiber is, the laser is somewhere in the plant, and then you have your long cable for 40 meters, and then you can work where you want to work.
Maybe this is the reason that Eric has 60 machines.
Yeah.
43 only, but yeah. I would say it depends also mainly on what kind of material should be processed. For example, when you want to process copper, when you want to weld copper, you need, with the infrared wavelength, very high power to get good results. When you want to weld steel, you need much lower power for this. And in this case, when I mentioned already copper welding, in this case, it could be useful to also have a green wavelength, but this is a new topic. It is also possible to get some tricks out of the infrared wavelength. This is a very, very big topic. It's not possible to just give an answer in one sentence, which power is the best for this application and the other application.
Okay. There is a question about the cleaning of aluminum before welding. Is there really something to say about it?
Yeah, I have given already an answer. The cleaning method for milled parts is normally an industrial washing process. If we use laser cutted parts, it is not necessary to add an extra cleaning process. If you want to work very, very clean, if you want to get the best results, it is useful to use acetone for cleaning the surface. So there are established washing processes when using a laser. Up to no washing necessary.
Okay, thank you very much, Eric. I see more questions, so I am a technical question for Professor Weber, please. In the car door example, the laser beam originated about 1 meter above the sample. What is the optics of the system? What is used to move the beam on the surface?
Of course, I'm well prepared to this question already. You might see my screen. Sorry, I have to find the. Of course, the film of Trump was continued. That's how it looks like inside. So here at the top is the light cable, is the fiber, the light guiding fiber. It's coupled with some plug to the optics. Steering mirror is not necessary. And you have a scanner. You have the small 2 mirrors that Eric was mentioning already. You have special optics here, f-theta usually it's called. And then it's a nice animation. That's why I can show it. You go to these 2 steering mirrors. And the idea behind the whole thing is that the robot is moving the optics very slow, because robots are not precise and robots are not fast, especially around corners. And here you use this steering mirror. And of course, this is, let's say, the most simple and primitive version of what Eyal is doing. So if you have the right laser, you don't need this, you just can use the laser itself. But this is the idea. And the focusing distance is usually between about 60 centimeters and 1 meter in this range.
Okay, the next question. Thank you very much, of course. For Rudy again, have you been able to eliminate hot cracks at the bottom of the weld in aluminum, magnesium, silicon alloy without the use of filler material?
So the answer is sometimes.
Okay.
This close, of course, Mr. Lammers exactly knows what the problems are. And there is, if you want, so maybe you still see my screen. This is this Novelis fusion material. There we have a silicon-rich layer on the top and the bottom. And if you make laser welding, you can very nicely distribute the silicon, and then hot cracking is diminished. Hot cracking is partly from the process, partly from the material, and the process can do something, the material can do another thing. Just one additional remark, there was a PhD student at the IFSW who, let's say, mainly solved the problem. If you do stitching it always takes or needs a few distance until you get the hot crack. So we do some stitching. If you stop the process before the crack appears, you can really get nice and crack-free welds. That's possible by the process, but by taking these multi-core fibers or so, at least we didn't succeed in doing it.
Thank you, Rudy.
Yeah.
Eyal, a question for you. Where it is? Eyal. Is there a numerical limit on the beam shape changes? Like, for example, the Corona laser from Enlight with 13.4 million beam shape changes?
No, there's no limit. You can do whatever shape you want, and you can change it as often as you want. Actually, I'm not sure I understand what is the 13 million come from, but you know, if you change it, let's say at megahertz, it means you change it 1 million times every second. So after 1 minute, you change it 60 million times. So there's no limit.
Okay. Thank you, Eyal. The last question from the audience, but I hope you will let me give you also ask some question of ourselves, okay? For Eyal, what is the maximum thickness you can get with titanium alloy? I understand the welding penetration. For Eyal, maximum thickness, it should be the weld.
I don't know. We don't know the answer, but you know, it really depends on what's required. Like I said, we have extreme high power lasers, so we have to test it. Maybe Professor Weber actually knows.
If you have enough power, you can get very deep welds.
Yeah.
There were welds in Japan, 100 kilowatt IPG laser, some 10 centimeter or even more. Exactly. So it depends on the application, of course. Do you allow me to answer the question of Mr. Lammers again? He was at the answered 5. He had a question how fast, how the power increase was, and allow me to show another slide again, because I have to film to what Eric Punzel was showing, and if I share the screen here, you can see what happens. So this is what usually, this is also an answer to another question. A few kilowatt for a few meter per minute, and then you get these ugly welds. And what you need to do is you need to increase the power by a factor of 5 and the feed by a factor of 10. So the efficiency is getting better. Anyway, so we went up to 16 kilowatts, 30 meter per minute, and then we had this weld. It's about the same welding depth. It's this nice capillary with U shape. Everything is more or less perfect stable. So you see it's about a factor of 5 in power and about a factor of 10 in feed rate.
With this regard, Rudy, thank you. With this regard, I would like to ask you, there is no limit for penetration, weld penetration, because how can you stabilize the keyhole?
Yeah, the stabilizing is always the problem. Even also if you get fast, if you move much faster, you get the phenomenon called humping, which means you have a surface which looks like you have a lot of bumps on it. Also, if the keyhole is deep, it must be big enough. You have seen this emerging vapor. If it's too narrow, you get a lot of instabilities. If you make the keyhole wider, you can make the thing stable even if it's deep. And this is also one of the reasons, I mean, of course, Eyal is here, but I would tell it also if he was not here. This is the reason why you need to shape the beam. You need to have fast possibility to adapt the beam shape, the focus position, that you can create a stable system. Otherwise, if you cannot make the capillary open, also Eric has shown, if the capillary has enough opening that you don't get this narrow parts where if it getting narrow, you shade the laser, then it's getting cold below. It sucks air in, making pores. So you really need to adapt everything in a first attempt just by doing something periodically. What Eyal has shown, the next step will then be you measure at certain points what you want to know, the depths, the widths, or whatever, and then you adaptively control the laser. This is the next step, Eyal. That's where we must go, really. Yes. And
but
I'm convinced of it. Sorry, even if he's here, I'm convinced of the concept of having such lasers.
Yeah, but there is a limit also for the welding speed. Otherwise, you need a very high power laser.
Yeah, of course. But there is no limit too. You can buy 130 kilowatts at IPG, actually. 130. That's quite a lot. But there's no limit. That will go to 1 megawatt.
You think no limit. You can still have a stable keyhole all along the day.
You need to adapt everything, but it's
okay.
Nice.
Okay, another question, please. What about the process gas? You ignore it. Yeah. It should be also a factor, a big factor in controlling the stabilization of the keyhole.
Eric, you are the application guy.
Eric.
Again, it depends on the material. Indeed, for aluminum, it is not necessary to use process gas, but for steel or especially also for copper, it is necessary to use process gas for cooling down the surface and for avoid the heating colors in steel, for example, and also in copper. But in aluminum, it's mostly we don't use processing gas for this.
No oxidation?
Aluminum has a natural oxidation at the surface, and this oxidation zone gets created within milliseconds. It's always there.
Yeah, but it is not produced during the process?
After that process.
It is high temperature and the aluminum should
after that process, it gets produced again. Of course, we have always a thin oxidation area at the surface of aluminum. But during the welding, as soon as we came into the material, of course, there will be some other chemical reactions, some processes, but there are more significant process windows to check for having a stable keyhole.
Okay, I got, thank you very much. We discussed welding. What other application can most benefit from beam shaping and steering? Eyal told us about the drilling and or in cutting, maybe other applications.
Well, in additive manufacturing, beam shaping is very, very important. To handle the powder, if you want to do additive manufacturing using powder, the control of the melt pool is very, very important, both for the quality of the part, as well as if you want to try to increase the speed. Again, you want to control the melt pool in order to be able to put more power without actually having a spatter and things like that. So controlling the shape of the melt pool and the dynamics of the melt pool is very, very important in additive manufacturing. And we see it as a very important market because additive manufacturing, as everybody knows, is a real revolution in the way we do things. However, today it's still not fast enough. And because it's not fast enough, it makes every part expensive. But if you can make it 20 times faster, it's going to make a significant difference. And we think that beam shaping can help that.
One question from a colleague is that we have heard about the benefits and possibilities of beam shaping and steering. What is your opinion? When would you recommend to use beam shaping over standard laser, standard beam?
When it doesn't cost more. When you get the same price, you get the capability to shape, then the constant is dead. And if it's expensive like it is now, still possibly, I do not know the prices to be honest, but I guess it's more expensive. Then you need an application where you can refinance it, of course. So if you have a critical application where you need to avoid spattering, all these new applications with electromotors and so, then it's very critical if you have spatter somewhere which make electrical shortcuts. Then it might make sense to invest a little bit more in the laser because then the post-processing is much more expensive than the invest in the beginning. So I think this is just a question of time that most of the lasers will have this capability. Whether it's the laser itself or it's an optical system which is put behind the laser, but I think this is only a question of a few years and then everything is like this.
You have studied the stability and the keyhole and the capillary. What about conduction welding? What would be the role of the laser shaping in this regard? We are not talking. We are talking only on melt, without any gas.
When I can say something about it, conduction mode welding is what I would call the nice welding. So mostly we have already a very nice, very high quality weld seam. So therefore we don't need necessarily beam shaping at conduction mode welding. It gives us the big benefits when we need to weld deep, when we go into the deep welding regime. Then the beam shaping gets important. And there are maybe a few possibilities, a few applications with deep welding where we don't need beam shaping. But for BBW, for example, we have at one day one product in our machine, in the other day we have another product. So this means when we have a laser source without the possibility of beam shaping, we can use this laser machine only for some application, but we would be very limited in, and of course we have some laser machines without beam shaping, and yeah, we are limited there what we can weld there. So steel welding applications, there are some applications where you don't need beam shaping, but copper, of course, copper and infrared wavelength, you can't weld copper very well without a beam shaping solution. And aluminum, of course, it's possible with high-speed welding, okay, but at low speed, when you need to weld deep, you need also to go into a beam shape solution.
Thank you.
But, okay, the question conduction mode, I would say it's not necessarily possible, necessary.
Are we going to throw the other lasers now from the market? Or we can modulate the standard laser to have beam shaping?
There is some approaches, yeah. Sorry, Eyal knows it, of course.
Yeah, no. I mean, so I think it was demonstrated here that you can do it with mechanical, different types of mechanics or optics can be done, just with some limitations. So, but the basic methods are available.
So what Professor Weber and I have showed in the presentation was you need a scanner for wobbling technology. You need a special fiber for the 2-in-1 solution. And then I have showed also the double focus technology. Then you need another special optic for this. And what I have seen from Civan, it looks like an all-in-one solution.
All-in-one.
Yeah.
Thank you, Eric. You are talking about autogenous welding. What about wire filler? Do you consider these processes?
So we actually have a customer who requires wire filler. We are not the expert in material processing. We just provide the lasers, so we do what we are asked for. So I cannot comment too much. I just know that the customer did ask for it. There's also interesting application in additive manufacturing, wire additive manufacturing, DED, where again, our laser is being tried with something like that. So, you know, again, we believe, for example, when you have the wire, there is a big inequality between the mass of the wire and the mass of the part. So if you have a part that's very big and you have a wire that's very small, you have to adjust the energy to get a good weld between the wire and the part. So we think that maybe the dynamic beam can also do something over there, but we didn't try it yet.
How does it go with the penetration welding? The wire and the material, the base material.
So exactly, that's exactly the issue. I think that if you have like a big mass of material and you want to add some wire, you have to make sure that that you do some melting of the material that has a big heat capacity and so on, and also of the wire, which is actually melts much faster. So that's where we think maybe with the dynamic beam, we can, so to speak, divide the energy in such a way to get a good balance that the material, you know, the bulk material would get some melting before the wire actually, you know, completely disappears. So, but this is just theory. We didn't actually do it yet, but we hope to be doing it in the next 6 months or so.
I'm just looking if we have some other question.
When I can say something about it, at the moment we have no application in our house with beam shape and the usage of wire, but I know one application where it's helpful. It's called the button welding. When you have a material with a big gap, for example, 1 millimeter gap between the two welding parts. I know that the Bias Bremen has showed this solution that you can use the wire and the wobbling technique to wobble in one dimensional above the wire, and you can fill the gap with this beam shaping. This is one application I know.
Okay. We're going to the end in 2 or 3 minutes, but still there is something which is very funny. Is there any formula to order in order to get the best welding?
Hard work.
And with minimum energy. Okay.
This is, by the way, you know, if you have minimum energy, you also usually get good welds. So there is some thermal efficiency, which can be not more than 50% in welding, because the rest of the heat is flowing away. And if you if you reach this efficiency, you also have good welds. So there is a relation in between having good welds and having good efficiency. That's good. That's the good news. Usually it's the other way around.
Thank you. Last question to Eyal. How do you keep the depth in the focus depth so large when you are shaping the beam? The shape of the beam should be less than Gaussian. So how it could be?
Yes, actually, it's a combination of two things. First of all, because it is a Gaussian beam, it has inherently a larger depth of focus compared to a multi-mode beam. So that's one thing by itself. But in addition, the whole concept of the adaptive optics or the optical phased array is that we control the phase across the wavefront. Now, when you control the phase across the wavefront, one thing is actually changing the focal distance. I mean, if we do a function like that of the phase on the wavefront, basically, effectively, is changing the focus. So we are actively changing the focus, just like a virtual lens. But this lens can change in nanoseconds according to our electronic control.
Okay, is there any other question or your comment? Do you have comments, speakers?
Do you allow me to answer very shortly two questions which I see still are open? One is funny. Somebody is asking after electron beam welding that there was always oscillations already. We are actually planning a project together with Aachen at WTH to compare the benefits of the wobbling in done with electron beams and see where the limits are, what the laser must be capable of. So I know they also have good quality. That's why we of course also look in the direction of electron beam welding. We want to avoid the vacuum, it's clear, but we hope that we can achieve similar quality by doing the correct adapted beams. And the second thing was the undercut and underfill. This is a serious problem. This depends on the process parameters, on the material thickness, on everything. Difficult to avoid. One of the simpler means is to avoid full penetration welding and to go into partial penetration welding. Then usually you don't have that much lack of material. And if you have really stable welds and additionally you have control, weld depth control with coherence tomography or so, you can avoid that you need to make through weld. Through welding is only a means to see that the weld is good. But if you have other means to see the weld is good, you don't need through welds, and then you also partly can avoid such problems.
Is it not affected by the process gas?
Also, yes. By the Marangoni stuff. I explained, yes. If you change this Marangoni flow, you can also change undercut and overcut a little bit. Yeah. So you can influence by the surface tension, by changing the surface tension locally. Yeah.
Okay, any comments, questions? I think we can conclude. It was very, very interesting evening, and I hope to have the opportunity in the future to meet again and to hear about the new things that you are doing and how you're proceeding with this. So thank you, the audience. Thank you, the speakers, for very, very interesting presentation.
Next time in Jerusalem, huh?
Yeah.
Okay, thank you.
Thanks a lot.
Thank you very much.
See you again.
See you.
Thank you for everybody.